It's really a wonderful pleasure to have Jonathan here, an old friend of many of ours. And he's going to be telling us about Cobordism Utopia, an attainable meeting of asymptotic manifolds.
Okay, so first let me say thanks very much for the invitation to come and visit. It's always nice to come. So what I'm going to be telling you about is hopefully something that will be done relatively soon. This one took a little bit longer than I anticipated anyway, so give or take a few months, hopefully. So it's with a graduate student at Penn, Noah Braeger, a mathematician who's now at Kentucky, Arun Debray, Marcus Dierigl, who's at CERN, and Miguel Montero, who's at IFT in Madrid. And it's also based on some earlier work that appeared with some subset of those people and an even smaller subset. And I'll be referring to some of this as I go. So I'll call this one, so this one will be referred to as kind of Utopia project for reasons that will hopefully become clear. It's going to involve the classic U-dualities that we have in the context of M-theory. And this one is going to be, I'll refer to as Concordia. I'm going to apologize to Greg because I think you've already heard this version of this talk already. So I'm sorry, you'll be bored. So this one I'm going to mention is motivated, but there's already classic dualities that take place in type 2B string theory, and there's interesting cobordisms that take place. Those will be kind of, that's the background. The motivation for looking at this class of questions has to do with asking about gravity and the expectation that there's no global symmetries. So of course, global symmetries are very helpful in the context of analyzing various aspects of quantum field theories. But in the context of quantum gravity, there is an expectation that they are not present. And so the question is, how would you get rid of them in some way? Or what happens? What is the fate of these things once we take a field theory of some sort and couple it to gravity? So from a bottom-up point of view, I'll try to be a bit qualitative here. I'm going to focus primarily on kind of a top-down point of view. Well, top-down is loosely interpreted, but from a bottom-up point of view, there's kind of two things you might try to do. One is in the context of gauging symmetry, and the other is in the context of, say, breaking a symmetry. Now, already you can ask, okay, what exactly do you mean by a global symmetry, and what is the sense in which it can be gauged or broken? So to illustrate that, it may not be as simple or as clear-cut as you might like to think. In the context of global symmetries, put it over here, there have been some very interesting generalizations, quite literally, of the way we think about what a global symmetry is. So, for example, one of the kind of key ideas, or one of the things that's appeared prominently, is having things like extended defects or lines, or more higher dimensional things. Maybe there's O, maybe they're supported over some p-dimensional subspace like this. There'll be some extended out. Of course, it could also just be localized at some point. But in principle, I could talk about, say, a Wilson line or surface object or something like this. And then the action of a symmetry on it can be nicely characterized in terms of some other thing which links with it. I'll write this. Links or sometimes intersects. And the idea is that we want these two things to link, sometimes intersect. This is the starting point for talking about, say, a p-form symmetry operator acting on, say, some p-dimensional extended object. And so when we want to have, say, the symmetry act, we just shrink it down. And this is some topological thing. Doesn't really care about metric coupling. Okay, so from this point of view, there are various kinds of generalizations that have been proposed. So for example, this thing itself has actually kind of come to life, if you like. It starts to carry interesting topological field theory attached to its world volume. And so if you start fusing them and taking products and other lower dimensional symmetry operators start getting produced, it becomes a much more complicated affair to say exactly what is happening, kind of gauging or breaking of these kinds of symmetries. So what I'm going to do is try to, so that's in the context of just global symmetries. And then of course, gauging and breaking in the context of coupling and gravity, you can ask, well, what happens to them in that context? So I'll come back to the kind of bottom up point of view and how it fits with this. But now what I'm going to do is explain how some of these questions are starting to be addressed from a top down point of view in terms of building explicit examples of quantum field theories, trying to couple them to gravity, identifying the relevant defects and symmetry operators, and then tracking what happens or what we even mean by gauging and breaking in these contexts. Okay, so from a top-down point of view, I know of basically 4 qualitatively different ways of approaching this. If you have another one, I'd be happy to hear it. So from a top-down point of view, one way you might imagine doing this is to first of all build in the context of, say, string theory or some explicit string theory background. You might imagine engineering an interesting quantum field theory localized in some patch, some small patch inside of an extra dimensional geometry. So from that point of view, you could draw something like this, and then the quantum field theory degrees of freedom localized here. And so, for example, things we now know how to do in this context are, first of all, to identify certain kinds of extended objects and the symmetry operators that come with them. And essentially, the kind of slogan is that defects and the symmetry operators, basically, this is what the OMP lists to. And then there's some topological linking involving the symmetry operator. Yes, this is what the UMQ lists to. So there's kind of a linking that takes place also in the extra dimensional geometry, which is complemented by this linking that's taking place in space. So you should think about this as the extra dimensions. And then there's some D-1 space-time where the field theory is living. Okay, so this is one approach to, first of all, building the global symmetries and then watching what happens to the defects and symmetry operators. And what would it mean to couple to gravity? Just stick this thing inside of a compact geometry and watch what happens to all of the objects that we've written down. So, of course, there's many choices for how you glue in. So that,
before you continue this,
yes, please.
U that you have here in the extra dimension, that's not the brain in the theory, right? That's
it is. It is a brain, but it's so the reason why it's topological is it's pushed very far away from where any of the action for the QFT is located. So it doesn't contribute to the local stress energy. So the only thing that's left over is some kind of branch cut type phenomena or some Aronoff-Bohm phases.
So you say just the ordinary brain of gravity when you put it.
That's right. So it's actually really crucial that it's a non-compact geometry so that I can push it all the way out.
Okay.
And that's exactly what will fail once I couple to gravity. I glue it in, and now it's a dynamical fluctuating thing.
So your P-form symmetries correspond to the compact use that you've drawn vertically. That's the wiggly line that went from left to right.
So this is the defect,
Yes.
and this is the
That's the
symmetry.
defect whose charge you're measuring.
Yes, and this is the symmetry operator acting upon the defect. Yes. By the way, I'm happy to switch gears and give a different talk if you prefer I not talk about cobordisms. Okay, so that's a nice story that's been developed, and we now know actually how to do this, not just for kind of like standard D-brains that have been around forever, but also for more intricate objects that come from, say, diffeomorphisms involving the extra dimensions, things that don't necessarily look like just straight brains. You can now kind of build different kinds of defects and symmetry operators. And you can study, for example, what happens when you take products of these symmetry operators or more complicated theories that may be completely strongly coupled. So this is just one approach to asking what happens. And kind of the quick answer to, well, what happens to the things is symmetry operators become dynamical brains, the defects become dynamical objects as well. So everything is dynamical by the time we're done.
And the moment it's dynamical, it's not topological,
It's not a global symmetry. So the laziest answer you can give about, do you have a global symmetry? Well, it's not topological anymore, so what do you want me to do? Right. So that's an answer that you can give.
When we want to answer whether it's broken or gauged.
Right. So that requires us to say more about whether this, for example, wraps like a compact, a cycle that survives inside of the compact geometry. So you can have situations where the local topology gets trivialized once you glue it into the bulk. And so what we have to do is take this cycle here and perhaps the defect might wrap around, say something in the bulk, or it might be trivial in the bulk. And those are situations where it will either get gauged or broken.
The trivial is when it's gauged.
Yeah. Or it could be like metastable and it gets broken. So it could actually live for a long time and then eventually kind of unwrap. So that's another situation.
Sorry, when the cycle is trivial, isn't that when it's broken?
So it can be broken. Yeah, so maybe I said it backwards. Yeah, so when it's just trivial like this, it will eventually unwrap and then it will get broken. So I think I said it backwards in answering your question. And then if it's wrapped, then indeed there's still something that's kind of floating around and there will still be something that has a gauge symmetry associated to it. Okay, so that's I'll call that approach number one. Now related to that, as everyone knows, you can take a singularity of appropriate type, put a bunch of branes near it, produce a near horizon geometry, produce examples of ADS CFT pairs and things like that. And you could ask from that point of view, suppose we have, say, a large NCFT, some kind. So I'll draw it over here. And let's imagine that, okay, so for me, ADS is just going to be some ball with a boundary. You can ask a question like, well, suppose I have in my CFT, there's no problem having global symmetries in a CFT. I'll draw this picture again with the operating and some linking. What we can ask is what happens to these objects, or what is the gravity dual to each of these things? What is the gravity dual to the defect? What is the gravity dual to the symmetry operator? And again, the point, or what's been established in many cases of interest is that basically this thing turns into a dynamical brane, but by the time, if you try to push it back to the boundary, then kind of the fluctuating pieces of it get suppressed out, and all you're left with is kind of the topological terms of the brane action. So you have a picture like this, and then it links. This is another approach, and again, the kind of the very short slogan is that this thing that's topological on the boundary is no longer fully topological in bulk. It's coupling to local metric fluctuations. Okay. So another way of saying it is that the candidate symmetry operator is not really topological. So again, this is going to that point. And you can kind of match this picture with this picture in various cases. Why? Because you just basically start focusing on local patches of that. Okay, so another,
Sorry,
yes.
could you say, I got a little lost.
Yeah.
Could you say again how this becomes topological? So there is some brain in the bulk, right?
Right, so there's a term in the DBI action. So let's just work in local Poincare coordinates or something. So we'll have, let me call that the metric or something. So if I look in the DBI action, there's a term. Well, let's say it's just like a D-brain. So there's the pullback of the metric.
Okay, I understand there is this term, but I'm just a little lost about the statement. I mean, I'm used to the statement that the global symmetries on the boundary are related to gauge symmetries in the bulk.
Correct, yeah.
They're the gauge symmetries that vanish at the boundary.
Right, so
That they are topological. Well,
yeah, but so for example, I'll give you, say, a Wilson line of the boundary theory. Say, well, what does this correspond to in the bulk? So in the boundary theory, we have a Wilson line, and we can talk about, say, a one-form symmetry operator, which links with that thing, and just in the boundary theory. Okay, so there's some Z mod in that we want to talk about. So now we say, let's lift the defect, the Wilson line, into the bulk picture. Let's also ask about what happens to the symmetry operator and what its link, whether it maintains this linking as we kind of talk in the bulk. So for the defect, we just lift it to, say, a string or something. As you know, we lift this to a string, and we ask what is linking with that thing in the bulk. So there's some other brane which is linking with it.
I would have thought that the statement would be that there is some gauge symmetry in the bulk. Which,
Yeah.
Form or whatever. And then
Yeah.
that.
That's right. There's a gauge symmetry.
A global symmetry at the boundary.
Yes.
Not necessarily some other.
Yes, but what I'm asking about is I have this symmetry operator in the boundary theory. My only question here is what happens to it in the bulk? Is there a dual object in the bulk? Or that
I would
symmetry?
say there is no dual object. There is just a gauge symmetry in the bulk that becomes this global symmetry.
Well, I don't know. That's not.
Well, maybe.
Yes, please.
So, I mean, the arguments that one usually hears about saying that there were no global symmetries in gravity make use of causal structure and or black holes. So is this meant to be an alternative?
So it's related more to kind of causal structure. And so these statements here involved, well, the argument that I kind of.
I don't see discussions of causal diamonds and stuff like that.
No, it's more has to do with kind of a smearing type effect once you kind of push it into the ball. It's more that kind of thing. So you look at what happens to something that's linked over here, and then you ask what happens as we start smearing things out as we kind of, so we introduce a small cutoff and we start smearing it out and we watch what happens with linking. That's
Not meant to be an I got the impression that this is a totally
It's not-
way of approaching this claim.
It's not completely distinct from the causal structure statement, but it can be phrased in Euclidean signature, so it's not. Yeah. Okay, so that's approach number 2. Approach number 3 is you could ask about, well, asking about what you mean by gauging some of these other symmetries is not always totally obvious. So it's not even well defined always to say, oh, so for example, one of the more complicated ones is talk about so-called non-invertible symmetries. And you could ask, what do you mean by gauging such a symmetry? Is there a gauge field or what is going on with this? So sometimes you can answer that question, especially for like a finite group, but it becomes more complicated when it's analog, let's say a continuous you want about what you would mean by gauging it. So to address that, you might say, well, I know a way to approach these kinds of questions. Give me a global symmetry, say in the world sheet. I expect that global symmetries of the world sheet will become gauged in the target space. So I'll just track it through that. And in particular, I can talk about one of these topological operators now on the world sheet, and then ask what happens to it. So this is another approach. And then the one I'm going to focus on, or emphasize a bit more, involves so-called cobordisms, which at first sounds like it's not completely connected in a direct way with any of the ones I talked about previously. So just to kind of set the stage, the idea is that we have different kinds of manifolds. And there's some kind of bulk W that has, say, 2 boundaries, and we say that M and N are cobordant, and we can define then a equivalence relation, just refer to the equivalence class. And this becomes very interesting because you can equip these manifolds with different kinds of structures. So you might want to preserve, say, certain kinds of duality symmetries, certain spin structures, things like that. And then the classes, the equivalence classes will move around with you. Now, as I'll explain, this one, if you have non-trivial cobordism classes, tends to tell you that you do have a global symmetry of some kind floating around. And then the question is, well, how do you get rid of it? That's where I'm going to spend some time. So to explain what cobordisms have to do with kind of this breaking statement or something like it, let's ask the following question. Is there an easy way for me to kind of get rid of this topological linking? So one way we can think about it is in terms of what we might call breaking, or perhaps a more apt name is screening. So imagine that at some higher scale, our theory wasn't just the one we had. Suppose we start adding new states into the theory. Okay, so imagine this is, for example, a line operator of Maxwell theory, and then at higher energies, I start introducing charge Q electrons or something like that into the theory. Now, what's different about that? Well, now some of my lines that I previously had can now terminate on those dynamical. So, for example, if I have such a dynamical state, so let's add a new state. And we're just doing this by hand to see what will happen to our linkings and so on. So let's add a new state. Now it can terminate. And now let's run the same analysis involving the line and the symmetry operator. Well, now the candidate symmetry operators won't link in the same way. Why? Because you just pull it off. So pull it up and I can deform it. It's supposed to be topological, so it shouldn't care where I move it around. And I can slip it completely off the top of the thing. So for example, if I add so this one over here in Maxwell theory. So just this theory, nothing else, just this one U1 gauge field in 4 dimensions. If I now add a charge Q state, so if I just had this, then I would have continuous 1. And if I add the charge Q state, then it's broken. So for screen, this is ZYQ. Okay, so this is from, again, from a bottom-up point of view. So I've just decided that I want to add things in my theory in order to see if I can get rid of. Now, gauging turns out to be even more slippery from this point of view. So often what happens, I'm not going to write it on the board, but often what happens when you have a finite P-form symmetry and you gauge it is you wind up getting a magnetic dual Q-form symmetry, which is global. So you're kind of in a bind about getting rid of all the symmetry, all the global symmetries. If you gauge one of them, you just pop out a new one frame. So you're going to have to add a new state from that point of view to break or screen one of those things, either the electric form symmetry or the magnetic one. Okay, so now what does any of this have to do with the number 4, cobordism, the one I'm going to be focusing on? Okay, so what does this have to do? Consider so let's imagine we have some d-dimensional theory of ability. And let's imagine that we've got our favorite, symmetry structure. Maybe it's a duality type symmetry or something like that, some spin structure. I don't know, whatever you want to equip these things with. Now let's say that we have some bundle. So here's my k-dimensional manifold, I equip a bundle. If I look at this thing, what I can do is let's just imagine we're on RD. I can use the existence of this non-trivial Cobordism class to start building an interesting defect in the d-dimensional theory. So to illustrate, let me draw. This one is R K plus 1. And this will be R. I'm not paying too much attention to the metric, I guess. B minus K plus 1. Now what I'm going to do is glue this k-dimensional manifold into some little tiny. So here's my picture of K. The point is that from the point of view of this d-dimensional theory, it looks like I've got some defect filling more B minus K plus 1. Okay, so this is the analog of, say, our line operator or something like that. And it's carrying a charge. It's carrying a global symmetry charge. How come? Well, because I told you there's a non-trivial equivalence class up here. In fact, there's a group associated to these things, which we often denote as omega, let's say it's for K. So the equivalent, the group of these things, there will be some symmetry structure on it. I'll just be a little bit, there's more precise ways to denote this, but I'll just write it like this for the purposes of the talk. It's some finite, this is some group. And what we've just built is a defect charged under, well, it's really assigning numbers, so it's actually going from here to the units. So this is some P-form symmetry, so P is equal to U minus K plus 1, acting upon. So we built a global symmetry, we built a defect, and we built a global symmetry, which acts upon the defect.
Sorry, what determines this group omega K? Is it?
Oh, that's the statement about what fundamental theory we're talking about. So I'll give you some explicit examples in just a bit. But for now, the statement is that typically you'll find that omega kg is not always trivial. It's often non-trivial. It has non-trivial structure. So I'll give you some explicit examples in just a bit.
You defined abstractly the symmetry group, but you didn't have a physical realization of elements of it.
That's right. You mean like what are the actual generators and so on, or did I build you an actual background?
In some of your previous stories, group elements corresponded to brains.
Correct.
Here you can say that you have an element of home,
Yeah, that's right. So right now it's incredibly abstract statement. I'm just setting up the motivation for what's about to come, which is indeed like, it's a bit unsatisfying. You'd like to say, well, okay, what is M? Can I give you an explicit background, that sort of thing. So I'll come to that in just a moment. So now I'm ready to kind of state something related to swampland. Okay, so this is the, yes, please.
It's related, but these are the charted defects, but how do you think of symmetry operators?
Oh, yeah, I don't actually know how to answer that question in these cases, just.
That was actually what the question I tried to answer.
Okay,
There isn't a nice realization.
right, so I'm gonna be focusing on just the defect part of the story, yeah. We have been thinking about how to fit story 4 with stories 1 and 2 a little bit more, but I have nothing concrete to say at the moment, so I won't,
If you did, it would tend to show that the cobordism groups really were symmetries, which you don't need to show.
well, yeah, but you might imagine taking some decoupling limit where pieces of it survive, so that's the case in which there might be something a little bit sharper to say, but I agree, like, you're not expecting a symmetry operator when you're coupled to gravity, but indeed in limits, maybe something good will happen. Okay, so
Be a little more precise about what this picture means. Are you taking a connected sum of MK with a sphere, a k-dimensional sphere inside of k plus 1?
right, so I'm,
having trouble just trying to.
so this is some point like defect, so just imagine this was like R2, this will just sit at some point in this space. So we're gluing it in, so we have a tube, and we're gluing it in, like,
So it's like a circle.
Yeah.
I see.
yeah. And as long as you give me a generator here, then I get to play this game, and then I get to build you a defect, and then I get to build you a global symmetry. Now, this is kind of the setup or the motivation for this swampland, okay, I'm gonna get rid of this. This swampland cobordism conjecture. That was proposed in okay, a long time ago by Heckman and Papa. And so what they asserted, okay, so I'll just write what they said on the board and I'll explain why it connects to this. What they asserted, okay, so this is their statement. The Cobordism group of quantum gravity could be true. So I'll just write K or for all K or whatever. Okay. Now, there is no definition of this thing here. So this is their statement though. So you might say, well, how can you talk about an object that you don't even know how to define? So that in quotes. The mileage from this kind of statement comes from saying that, well, if you calculate that you got a non-zero Cobordism group, you are predicting the existence of some kind of extra dynamical state or some extra object to start trivializing the Cobordism group. So similar to how we took Maxwell theory, we had lines. We're going to add electrons to kind of start breaking the P-form symmetry. The expectation is that if I can build you this defect, there should be some kind of dynamical state which trivializes or starts breaking those symmetries. So this is why this is a very interesting statement, because you can go out and you can ask your mathematician friends. So our mathematician friend is in the room. And we can ask for help in calculating these Cobordism groups. And often we get non-zero answers. And then you could say, well, that must mean there's some other state in the theory that was responsible for getting rid of the candidate global symmetry. The statement is, so there's a pictorial.
Is this equivalent to the statement that I should be able to connect any two vacua
Yes,
with some geometry? in the middle?
yes.
Is it the same statement?
It, morally, it is the same. I don't know if all the details are exactly the same, but yes, it's that statement.
So some non-trivial charge or something might obstruct doing it, but if there are no non-trivial charges, you can connect it.
Yeah. So for example, one that, well, we've been thinking about this, but I don't want to kind of say too much about it. You might, for example, ask, well, how about things like perturbative type 2A string theory and perturbative type 2B string theory? Is there a domain wall that kind of sits in between them? And the answer should be yes. How do you build it? Well, I don't know. But there are some ideas we've been thinking about on how to do exactly that with another set of folks. But that's more than probably a few months away. So So the picture you can draw about what they're saying, so this implies expect new objects. Dynamical objects, new dynamical objects. Okay, so what's the picture we can draw now? Well, I'm going to visualize it in terms of this MK. And then we can imagine filling out, say, one more direction, say a radial direction. So that we're going to view this as kind of the boundary of some space. I'm going to fill it in. And then there will be some new object. Say, so some Debray or something like that, or whatever, something like that. And McNamara and Boffa actually went through this thought process in the case of D-brains to see that, well, if you introduce a certain P-form potential, do you get the expected kind of dynamical state associated with that? Okay, great. All right, so there's some various checks we can do of this. So McNamara,
Is this new object supposed to be wrapping manifold coordinate MK or?
no, it's supposed to be filling the space-time here. So it's kind of like, so this is like the world line of the electron. So this is kind
I
of,
understand this picture. It looks like a cone, but it's not quite a cone.
well, so for example, in some cases, this will be the kind of the quote unquote world line of the electron, the dynamical state. And so what it's going to look like from this point of view is like a point-like thing that's canceling off the charge that we created from this new defect. So for example, to give an explicit example, suppose you had, say, R2. So at the boundary, its boundary looks like S1. We can put a real codimension 2 object here, and it's filling the rest of the directions. So this will be, say, a 7 brain of, say, type 2B or something like that. So that's the object we're expecting to produce. That's the analog of the kind of the world line of the electron, but now in this more complicated.
The M sub K would be the S1 MK?
Yes. That's it. Does that answer your question? Or okay. Okay, so now so this is a nice story to tell, but now you could ask, well, what kind of Cobordism groups are out there that we might expect to be present in, say, string theory or M-theory or something like that?
Confused on why we're, so in this quantum gravity case, this k-dimensional space is what is a submanifold. Are you thinking of both space, which is a product of two spaces, or? I'm a bit confused why we're talking about the submanifold. Maybe a codimension one manifold.
This one
Or
or
the omega case.
so this is going to be viewed as kind of living at kind of the boundary of your space.
Is our total the quantum gravity living in R2 or living in R10? Or
R10. It's R10. So in this particular case, it'll be. So we're imagining some 10-dimensional theory.
But the omega k would be omega 9.
No, it'll be omega 1 in this case because it's associated with a circle. So K tells me the dimension of the manifold. So it's telling me the dimension of the boundary manifold in this case. In this case, it's a circle. So for example, if I gave you a 7 brain, it fills 8 directions. So 7 plus 1. And then I wind a circle around that thing. That circle that I'm doing the winding with is going to be my omega 1. And then likewise, if I built you, say, I don't know, a 6 brain or something like this, it would be an omega 2. And I keep going down for the dimension that the space-time that the brain fills, and the omega k increases in dimension. Does that answer your question, or?
Right. I thought the cobordism is defined for manifolds of some dimension, right?
Yeah, but I need to do this for all k.
Is W physical or not? Or is it some mathematical discussion? I mean, the
I don't know. You could probably visualize it as like a tunneling process of some kind, but.
in that case, it would.
So when you say it's charged, I mean, is there something that measures that charge? Maybe this is the questions that were asked before. You say it's charged under Hom omega k g to 1. I mean, we know about Ramon fields. We know about the massless fields of supergravity.
Yeah.
Is it supposed to be charged under any of those, or?
Right. So let's take like, say, a P form potential or something like that. So I can build you an extended an extended line operator.
Right, but you're gonna write a bunch of torsion groups for various Gs. I mean, are these all supposed to be charged for
Yeah. So for example, for the remote,
supergravity?
for fields of supergravity,
When you say it's charged under.
well, okay, so in the sense,
What's the procedure for measuring the charge?
well, I build you the defect. And
Well, the defect's far away. How do I measure it? I mean, what's the analog of the gas law?
Isn't the answer that there isn't one, and that's why it's a global symmetry? You're going to get rid of?
yeah. Yeah, but
Well, but wait a second. What about the deep range? You said the deep range fit to this.
yeah, so take like
Measure
a,
the deep range with their Ramon charge.
so imagine you didn't know about D-brains. So you start with like, say, a P+1 form potential.
Yeah.
I will build you an extended defect operator with that thing.
Okay.
So now I say, okay, great. I want to talk about that defect. There's a nice symmetry, there's a nice global symmetry acting on that defect. I want to get rid of it. What could I do? I will introduce a dynamical state which terminates that P+1. That's the P spatial directions of the D-brane.
Right, but still I can integrate on a linking sphere at infinity, some Ramon field strength. And measure that charge. I'm asking what's the analog for all these other.
Yeah, that's the element inside of omega kg to the top.
How are we modifying supergravity to see, well. I mean, is there, is there some object we already know about in supergravity that we could measure some Aharonov-Bohm charge as we move it around?
So as I'll explain, sometimes you know about these objects already, and sometimes you don't. Right, so let me do a couple quick, let me explain what we did in the previous paper. So I already wrote some U-duality groups on the board. Hopefully I'll get to some of them. So in the case of 2B duality, what you can ask is, well, I'm going to start with some manifold, and I want to ask about equipping it with some duality bundle. So the first answer you might give to say, what is the duality group of type 2B is something like cell 2. But that's really only acting on, say, the bosonic content of the field. There's various lifts, Z2 lifts of this thing to a slightly more complicated structure, similar to how you would start with, say, SO3 and say lift it to SU2. So if you include, for example, fermions, you get a Z2 cover this thing. So the arrow is going the wrong way from the point of view of covering, but sometimes referred to as Z. And there's another way to go, which is basically include things like world chief orientation reversal and a dual cousin, a -1 to the FL function. And if you do that, you actually get to entertain things that have determinants of plus and minus. And if you include both of them, you get to this more complicated thing, plus cover. And what's interesting is that since you have the fermions in the game, there can be non-trivial correlations between the bundles you build here and the spin structures you stick on the various manifolds. So to just give an illustration of what you can now do, in context of, say, the MP2Z case, in the plus 2 case, you can go ahead and you can calculate. Okay, so you get Z mod 8 plus Z mod 3 in this case. And I'll explain what the interpretation of these two guys is in just a second. You get Z mod 2 and Z mod 2. Okay, so again, the picture is we're in 10 space-time dimensions because we're talking about type 2B. We have some bounding circle off at infinity, and then we have some objects sitting kind of in the middle. This is going to be associated with some candidate 7 brane. And the explicit geometry that realizes these things. So for these two, basically looks like the M1 that you're building. C cross Now, I've introduced a torus to help me track what's going on with, say, the SL2 and all of that. There's a nice story in kind of the non-perturbative lift of 2B F-theory, where what you do is you take the 10-dimensional space-time, and over each point, you basically decorate it by some torus. And that geometrically implements the SL2 that's acting on this, and you move that around, and the shape of the torus might do something interesting. And so I folded that into the discussion here. So now this is basically R8. It's filling these directions. And this is kind of the bulk geometry. And there's some quotient by a ZK. And this quotient is such that it has exactly one fixed point inside this complex line, right at kind of the origin. That's this point right here. So it's really a 7 brane. And then the different choices that you make for this ZK quotient dictate which of these two things you get. So from the point of view of the Ks that we're talking about, this is again an omega 1, but it's equipped with this bundle structure. I've just decided to geometrize it. So if you like, this is the boundary of this complex line with this group action is the thing that's quotient is the thing that's producing the circle. And then we have some bundle over here. Okay, and actually it turns out that many of the generators, even at higher omega K, basically work like that. So many work like boundaries of CM, what's this? Yeah, nice and appropriate. Right, now what is this Z mod 8 and Z mod 3? Actually, these are pretty important special values of a complexified parameter. So there's the axiodilaton of type 2B, the combination of an dilaton process, and under the SL2, it shifts like this, where this is some element inside of SL2. So what's going on here is that these guys here, the Z mod 8 is associated with one of the interesting magic points, if you like, of tau. It's one that's fixed under a subgroup of the full-blown SL2. Sorry, that's tau equals I. And then this one is tau equals I over 6. So these are just, so for example, tau equals I just tells you how like this, where a torus like that, and this one's some tilted. So these are actually well-known objects from the point of view of type 2B, and there's certain non-perturbative bound states of branes that have fixed values of this particular parameters. So interestingly enough, this Cobordism group seems to know about some of the 7 branes that we wanted to talk about from the point of view of just string theory. Now, how about over here? One of them survives. So basically, one of these Z mod 2 is the same as before. This is the tau equals I one. And there's different ways to talk about it, but it's basically a carryover from this case over here. This one is something qualitatively new. It does something which is a bit non-holomorphic. It's not even supersymmetric. What it does is if you wind around the circle, it sends, well, it does a bunch of things. One of them is that it sends tau to minus tau bar. So it flips the sign of C0. There's a minus and a tau bar, so it just flips the sign of C0. It also does other things. So for example, it also even acts on the 4-form potential, which couples to branes. It flips the sign of that one as well. And it does some other things as well. But the point is that this is some new kind of codimension 2 object you could talk about. And geometrically, what it's doing on this torus, let's just write down a square torus like this, is it's introducing a reflection as you kind of wind around the circle in the space-time. We refer to this as a reflection 7 brane for that reason. So basically, a bunch of these Cobordism generators match to kind of known string theory objects or known string theory backgrounds, except for ones that involve these kinds of funny reflections. So these ones don't apparently have, can't be built in the same way. There's no kind of known worldsheet way, and you shouldn't expect to find one. But they nevertheless seem to be present. So kind of one way to spin this is to say, well, we calculated a bunch of Cobordism groups, and we find that it matches to known string theory objects. That's an interesting check of what the Cobordism conjecture would be telling you. And conversely, if you just accept the Cobordism conjecture, then you seem to be getting a new object.
So I have a question here. So, and if you formulate orientifals using twisted equivariant K theory, then there's room in that classification for a two torsion, seven brain.
Yes, it is the same object that you had in your paper with Dan and Jack.
Yeah, but I don't know it's the same.
Well, it's, so you take,
I mean, there was some formulation in terms of K theory groups. What's the relationship to the?
well, but you can produce K theory classes from starting from this thing.
So is that what you're saying? Is
Yes.
use this construction to?
I'm pretty sure that, I mean, okay, we have not,
Did anybody do that?
nobody has done it from start to finish, but I think it's very, very likely that it's the object you guys talked about in part of,
Okay.
into the footnote of one of
You
your.
didn't have anything close to this, this elaborate classification.
No, but you did have the statement. So basically your statement is like, well, by completeness, I should expect there to be a charged object. So this is just some elaborate version of that.
Okay, yeah, but we had two torsion, seven brains, and maybe I think the domain wall between two A and two B.
Yes,
We didn't have anything like this.
no, but you did,
This
secretly did.
table of yours.
So for example, this guy here is coming from reflections.
Yeah,
That's related to these guys, which is what you had.
right. But what I'm saying is you've got lots more. So are we?
Oh, well, you mean like these things?
No, I'm thinking about the board above, that look above your hand. Yeah, you've got this whole incredible table of groups.
Oh, up
You're
there.
gonna basically tell us that there's objects associated with the generators of all those Cobordism.
Yeah. Oh, okay, well, actually, these are the most, but the ones,
Nothing to do with,
no, this part here does not have to do with what you did.
oh,
This part is separate. This is the, okay, I'm running out of time, but this was the warm up. And then what I was gonna do is tell you about the M-theory case, which is the U-dualities case up here. So this was just for the SL2 case.
oh, I see, these are gonna be, the one above your, up to the upper board are intrinsically M theoretic, and we shouldn't be seeing them in two B, is.
You can see parts, sorry, you can in principle see parts of it, it's like the SL2 up there. Yeah, you can see it in various ways. The one that we're talking about here with the GLs and the GL pluses, that involves some spin and pin plus lift of these things. I honestly don't know how to do the spin and pin plus lift for most of these GUs. But for the ones I do know, then yes, it should be basically the same story. But for example, for like D equals 7, SL5, I'm gonna be stuck at SL5 and not tell you the spin and pin.
But it's still not clear to me, are we supposed to see this also in K theory? Or not?
This one. That one's not so, that one's not so clear to me.
Okay.
Yeah, that's not clear to me. Yeah,
You said that it flips the sign of C naught and C4, does it flip the sign or roll?
so that depends on which flavor of reflection 7 brain I give you. So for example, there's an omega 7 brain and there's a -1 to the FL. If I pick the -1 to the FL one, then it will flip all the Ramon ones for sure. And then the other one will flip the B field, the NS2 form B field instead of the Ramon 2 field. Yeah. And then those two choices are S dual to one another. All right, so this was
Come back to find out, are you predicting particles that we didn't know about?
articles you didn't know about. Yeah, or instanton-like objects. Yes. Yes. Some of them do kind of sweep. This turns out to be kind of this and its cousins after compactifying are kind of the only new things. But yeah, it's a new object from that point of view. Yeah. Okay. Since time is a little bit short, okay, so in the context of, say, maximally supersymmetric supergravity theories, a thing that's been known for a long time is that there's an analogous thing you can talk about in terms of this type 2 duality. You can talk about these so-called U-dualities, duality groups. One way to visualize what you got, Let me erase a bit now. Okay, so this was Tubordia, what I just told you about, and Utopia is the follow-up to. Yeah. One way to produce these maximally supersymmetric gravity theories is to start up in 11 dimensions. So we have a supergravity theory, and so the M-theory, 11 dimensions, and we compactify on some little d-dimensional torus. We count here. So this is hidden from us. These are extra dimensions. And we're living here in this big d-dimensional space-time. So from this point of view, you can kind of spot some of the pieces of the U-duality group. So there's the large diffeomorphisms of the little d torus. So the analog of SL2, where the two torus now souped up to TD. And there's a little bit more because we also know that if you take M-theory on a little circle, you get down to type 2A, and that has interesting T-dualities. So not completely geometric things, now more complicated things. So I'm not going to explain this thing. You should think about this as some souped up version of semi-direct product where you have left and right fractals. So in terms of difficulty, direct product, semi-direct product, and then bow tie product. Diffeomorphisms and then dualities. And then these are the G sub U's that I wrote on the other board. Okay, so it's not quite fully geometric. Now you can make this thing geometric. Another route to producing some of it is to start, for example, in 10D and type 2B, and then go down on a D-1 torus instead of a D torus. And then you can geometrize some other pieces of it that are, say, in here instead of in here. But the full-blown thing is never completely geometrized in one particular ring. I should also say that the analog of the spin and pin plus lift, so they get the full-blown group, is not known as far as I know. I mean, I'd love to know it, but I don't. Okay, so I've written on the board what you can say about many of these cases. So these are all at kind of low values of omega k. So omega 1, it's like a bounding circle, and omega 2, a bounding 2 manifold. So in those cases, even though it looks like there's something complicated going on with the Z mod 2, most of that, morally speaking, has nothing to do with the duality group structure. It all has to do with the fact that I imposed like a spin structure. It's really more about cobordisms involving spin than anything to do with dualities. The Z mod 12s that you see over here in this column here, that's all due to the SL2 factors that are floating around at 10, 9, and 8. And then once you go above, go to lower dimensional things, you get more complicated groups, but actually the objects you get kind of all get killed off. So what did we do in this project? Up here soon. Well, we just started calculating for this thing, different values of okay. So focused on the first non-trivial case that we hadn't covered yet. It's like that. And we basically did this for k equals 1 up to 7. So in the case of 7, it's something that looks like an instanton inside the 8-dimensional spacetime. So it's totally point-like. You can also ask about, so it's also physically interesting to ask about 8 and 9. So 8 tells you about candidate discrete theta angles. So if you put your theory on this particular background, then you have to weight it with a sine or a phase. And 9 tells you about candidate anomalies. We did not fully do these cases. For one, probably the more interesting case to talk about is where you've got fermions more properly in the mix. And second of all, it just turns out that the Cobordism calculations are much harder in these cases, so we don't know the full answer. We know pieces of the answer, but it's just harder to Okay, so these are all done, and now I'm just going to give you an illustrative example explaining like one of the non-trivial cases. So since I'm interested in being in this case 8-dimensional backgrounds, there's different ways I might approach getting this thing. So what are the things you might imagine doing? As I said, you can imagine doing. This is one route to producing this thing. And just like we did in the Tubordia case, the idea is going to be to start talking about interesting 3 torus bundles over the 8-dimensional space to geometrize the SL3 duality bundle. So there's an SL3 acting on this T3, and we'll geometrize it in some way, this thing here, and that will give us a way to think about some of the generators for this Cobordism. There's another way to go, which is to start with this thing. So remember I had this distinguished F-theory torus, so my 10-dimensional spacetime is here. I can play with another torus here, and this will allow me to geometrize a different SL2 subset by acting either on this thing here or on this thing here. But in no way am I going to have one kind of 10-dimensional or 11-dimensional picture which captures the full-blown SL3 cross that SL2. So what's exciting about that is that in some of these cases, for sure you find Cobordism generators that involve both the SL3 and SL2. You're predicting then, from this point of view, some new kinds of non-perturbative objects which have to make use of all the SL3 plus SL2. So it's a new thing. Similar, not quite on the same footing as the reflection submarine, but it's one that's very hard to build from public property. And it's something that the folks, if you know the literature, doing exceptional field theory, they tried to geometrize these different U-dualities. It fits into that kind of picture. Interesting. Okay, so let me give one example. Stop. So the first non-trivial case. It's involving 3 manifolds. And it involves, okay, so it involves a bunch of different pieces. So it's actually a lot less messy than you might initially think. I'm going to focus on this one here, the Z mod 3. There's 3 of them. There's 3 Z mod 3s in play. I'm just going to focus on that one. You can do similar games for these and these. But just in the interest of time, let's look at that. Okay, so this is some 4-dimension 4 object. And also because 4 plus 4 equals 8, it fills 4 dimensions. All right, so 2 of them, 2 of the Z3 generators, focus on Z3. You can actually build in this 2B / F theory point of view, and they actually fit in the same kind of picture that I was telling you about earlier. One of them looks like this. And what does this look like? So we're using this, so it looks like 3 copies. You produce 3 local. So if you imagine looking locally in any little patch inside of the T2, there's 3 fixed points. And what you get is 3 copies of the C mod Z3. So it's a particular 4D n equals 2 thing that's living in these 4 directions. It's not a particularly interesting 4D theory, but this is kind of tied to the background. There's 3 of them. A little more interesting is if you swap the roles of the 2 tori. This one, it turns out, so be very brief with this. turns out this is a particular six-dimensional superconformal field theory wrapped on a space. And this in turn makes a particular 4D n equals 2. So an incredibly complicated quantum field theory is being produced to cancel the Cobordism generator. The next one is, and this was one you cannot see, or we don't know how to do it in type 2B, is built straight out of 3 torus.
With the n equal to 3 theories, right?
Yes, so in this thing, you can make n equals 3, like the so-called S folds. These are non-perturbative generalizations of orientafolds. Those guys are also generators in this Cobordism thing. So they also fall out. So yeah, they're there. There's n equals 3, and then there's like spin Z8 cousins of them that only preserve n equals 1 supersymmetry. So they both have to be there in the two Cobordism. Okay, so the last one is this thing here. And this one is built in a slightly more intricate way. So there's a particular monodromy acting on this T3. Here's what it looks like. You can check that that's inside of SL3. And what it looks like a little more carefully is 3, S1. So this all looks very similar to what we did over there, but then there's also a shifting that goes on. So what we do is we're visualizing the P3 is basically a big cube. We identify the sides, or if you like, you have 3. And then what's happening is you're going to shift by a particular lattice vector inside the C3, in addition to this. Now, I'm gonna spare you the geometric analysis of this thing and just tell you what you get. Basically, because you have these Z3s like this by itself will produce 3 5D conformal field theories. They would be so-called 0 SCFTs, that's never found a while ago. And then what happens by having this circle is that they're all kind of glued together. By this so again, it's a fairly complicated 4-dimensional thing that's actually being produced as a defect in order to cancel off the Cobordism group. Okay, so I'm almost out of time. So you can basically play the same story for this and this, and also for the lower case. In the general statement is that this is kind of the bulk. And so what we're typically producing is things that look like, so at the boundary, this thing looks like some sphere. And then what's happening is that we're quoting by that and we're equipping it with some complicated bundle, some duality bundle. Now, this is a nice part for K equals 3. Something interesting that happens is that basically starting at omega 5 and above, you start getting pieces that are really requiring the full-blown SL2 times SL3. So the thing that I had here is that basically I got away with just having the SL3 or just the SL2 switched on. So it didn't really require full-blown non-geometric stuff. And I could tell you, oh, this is a particular M-theory value. So especially in these cases, you're getting these T-folds. These are some non-perturbative things involving the full-blown duality bundle. Now, all of that is switched on in these cases. Okay, so
So when you say you have a T-fold, you mean a certain T-fold is a generator of this group?
yes. Well, so it's the thing that is being introduced to trivialize the Cobordism. Yeah. So in other words, the T-fold in this picture is sitting right over here. So it's the thing sourcing this sphere with the appropriate bundle on it. Yeah, and I mean, the most geometric way we know how to build it is this kind of, okay, it's a bit speculative, this exceptional field theory thing. This exceptional field theory thing doesn't work particularly well in curved backgrounds, as far as I can tell. For flat backgrounds, it's pretty good. So for cases where you don't switch on a complicated metric in the interior, it actually seems to do a pretty good job in producing nice solutions. Yeah, okay, so now let me I'll just quickly wrap up. I'll be done. Okay, so basically, what I told you about is some non-trivial checks of this Swampland Cobordism conjecture and reversing it as a way of kind of looking for new kinds of objects in order to break these candidates of global symmetry. Now, one of the things that I didn't talk about is that, so when I did this Maxwell theory example, I said, well, let's just add a very heavy electron to break or screen the higher form symmetry. All right, from that point of view, one thing you'd like to know is what's the mass of this electron? Well, so what is the mass of all of the objects that are stuck into the system? So question one, what is the tension? Slash mass. So this will require me to have some definition that applies to, so for example, I was using complicated quantum field theory stuck at the tip of a bone in order to, so I need to have some notion of tension or mass, which is capable of saying, yes, this is non-zero. A natural guess is that it involves something involving the stress tensor 2-point functions for the CFTs, because that's how I count degrees of freedom. But I don't know a more precise way to say that. A related question is that this is at some level, these calculations we're doing here is just some approximation to what we think is going to be the full-blown answer. Similar to in Tubordia, where what we did is here, basically the Utopia project is stuck over here at this SL2 approximation. There's all these things involving the fermions and the reflections and all that have not been taken into account. And kind of the bottleneck right now, well, I'm sure there's many more bottlenecks, but one of them is to just state what the appropriate spin or pin plus lift of the U-duality group is. I mean, apparently nobody bothered to work it out. I don't know. I don't know, maybe somebody knows it, but I don't. And then of course, if you had this, let's call that thing script G. Then of course, the next thing would be to calculate appropriate set of Cobordism groups. There's another place where the wheels are probably going to fall off. So I'm most optimistic about doing it for say D equals 8. That's the SL3 times SL2. There's pretty good guesses about what the answer is for spin and pin plus lift and so on. But even doing the Cobordism groups for E equals 76543 for this SL5 and so on, there's a couple of technical tricks that were really, really useful in this SL3 case. The analog of those statements is also not really known for SL5 or above. So again, so we kind of lucked out in D equals 8 because a few mathematicians, so for example, Soule and Minami have basically done some pieces of the calculation involving, so you can look at the group cohomologies for these SL3s and read off, they don't have the full answer, but you can read off pieces of the answer from that and then pull it out. For SL5 and above, I don't think anybody has touched it. So again, you're a little bit at sea in terms of getting that far out as well. So, I'm most optimistic.
How you computed these omegas?
Oh, so, yeah, so how much do you want to know?
Well, did you compute them or did someone else compute them?
So Arun was the one, so Arun and my student Noah were the ones who did, I would say, the bulk of the work in terms of calculating the Cobordism groups. Now, that's the part where there's kind of two main techniques that you can use to get those things. So there's two spectral sequences involved. So you should view these as kind of approximations to the answer and you hope that they converge to give you the right answer. So there's the Mattia Herkenbrook spectral sequence. And then there's also the Adams spectral sequence. Okay, so for these two, it turns out that there's one more trick that you can use. There's this thing called P local S equivalence, where even though you start with a really nasty looking group like this, you ask, what does it look like mod 2 or mod 3? then it turns out that the whole thing starts breaking up into much simpler objects that you can start manipulating. So the thing that these guys, Soulé and Minami, did is they tell you the answer, like how does it localize at prime 2 or prime 3 or so on. So using that, it turns out that at prime 3, everything can be captured through a Theta Hirzebruch, and then for prime 2, you can use atoms. Initially, the whole
local to global problem.
local to global problem.
If you're calculating them locally at the various primes, but
Yeah. No.
that doesn't mean you can get the global.
No, but there's it does just break up in this direct sum for these pieces.
So you're saying there's no local.
No, I don't think so. Not in this case. It turns out that these are actually the only primes that appear. So that's another thing you kind of just directly check. That's not actually true. That's another kind of annoyance about these other ones. So for example, for SL5, P equals 5, you might expect is going to appear, and it does. So it gets a bit more complicated from that point of view. But yeah, these were kind of the two things that you have to kind of feed into the machine. This one, just generally speaking, it's more about like vibration type structures that you have. This one was kind of the main workhorse for the Tubordia project, in particular because it involved all these Z-mod 2 lifts to get the spin and the pin plus lifts and so on. So that's for getting the groups. Now for the generators, it's another story because there's no kind of turn the crank algorithm available. And in many cases, what we had to do is say, well, this looks like a plausible string theory background. Does it work as a generator for this? And the way you check it is by looking at various kinds of topological invariants of the boundary manifold that you get from that particular string theory background and asking, does it match to pieces of the characteristic classes you see popping out of the spectral sequence arguments? So yeah, that's if you like how the division of label. So, okay, yeah, I guess I'll just stop there. So thanks very much, and that's it. Yes, please.
No, so you had a question, right? Q2. So you showed that capital G sub U is a bow tie of two groups with a geometric interpretation. And so since they have a geometric interpretation, surely the spin lift of those two factors can be, derived from the supergravity or.
Absolutely. And then the question is
how do they claim it? So you say it's not obvious that the bow tie of those lifts is the correct thing?
I want to say yes, but I'm not actually sure that there's a unique one always. So for some of them, yes, I think that is. So for example, for SL5, there's basically one answer that you can expect. But for example, for E77 and E88, I just don't know if there's like a unique way to kind of combine it. So indeed, your guess is the natural one. Like, well, you're clearly.
Okay, so I mean, with the semi-direct product, you need to choose an automorphism of one group acting on the other.
That's right. That's where all
the problem that there are the lifts, but there are many different ways of having an automorphism acting on one acting.
Yeah, that's in principle the worry. Now, I'm not saying it's an insurmountable worry. I mean, it's a doable thing. It's a doable thing.
So it sounds like there would be a finite set of possibilities.
Yes. Yes, there's one strategy which I've been advocating, which is we just write down by brute force all the candidates, and then we just start checking or start eliminating them. But it hasn't been done yet. That's all I'm saying. So this is a known unknowable or whatever. It's doable. Yeah.
I have a question, I think maybe restating Greg's question before. So these are all kind of like fancy brains that we didn't know about before, some of them, right?
Right.
So so what do they source far away? What do you see? What they have some tension, which we don't know.
Yeah.
What else?
Well, what we know, so for example, in some cases like this reflection 7 brain, we know what happens if we wind around it. So we can see that, for example, a D3 brain will turn into an anti-D3 brain if I wind it around. And I'll also see that tau goes to minus tau bar. And I can also, using these kinds of arguments, actually tell you things, well, what kinds of objects end or terminate on the brain. So for example, you can do these like topological lasso arguments. So if you have the brain like this, let's imagine its brain spread is like this. You can send a brain an object in. And because it's acting in some way, you can do this and you can cinch it off and then have it kind of attach. So based on this kind of argument, you say, well, I know that D3 branes can terminate on the R7. I know that, so this would also, by the way, suggest that there's a three-form potential living on this thing. You can also say, depending on which flavor of reflections on the brane, a fundamental string or a D1 brane end on this thing.
But it doesn't source other massless things other than gravity.
Well, there could be non-zero, non-trivial world volume degrees of freedom on the brane itself.
Right, but not far away.
No, not far away as far as I know, no.
And you don't know enough to like scatter things off of it or something from the outside. Or you don't know what the metric is, what the solution is.
We don't know that, but we do, but I think we can say more about scattering. So for example, in many cases, right, in the Aronoff-Bohm phase that you get is kind of the dominant. So imagine you're doing scattering off a cosmic string.
Sure.
The Aronoff-Bohm phase is a pretty helpful thing. That kind of thing, I think you could, because you're just checking like what happens to the phases that I pass through. So yeah, so that kind of thing, I think actually we do have some control over. Yeah.
Can you put them on top of each other?
Sometimes, so if you put two of these things on top, it just decays into radiation. So it's captured by a Z-mod 2 class. So,
Oh, I see.
so if you put two of them on top, then it just disappears into an unconserved gravitational
Do
radiation.
the 12s mean you could put 12 of them on top of each other?
Well, the 12 is, okay, so 12 is a little bit deceptive. You think about Z-mod 12 as Z-mod 3 plus Z-mod 4. And then you're back to roughly this kind of thing. But yeah. But yeah, in principle, you can just take like 12 or 24 of these things, stack them on top, and then watch that. Oh yes, actually, there's a Cobordism class which would trivialize it. Yeah. Those Z-mod 12s are the more kind of conventional 7 branes that F theorists knew about for a while. Yeah.
Any other questions for John? All right, if not, let's thank him for a beautiful talk.